Our next speaker is Professor HAMAOKA, and he will be talking from Keio University, and he'll be talking on Hiroshima, Nagasaki, Hanford, and Fukushima, a critical review and reanalysis of radiation epidemiological studies. Professor HAMAOKA, thank you.
じゃあどうもご紹介どうもありがとうございました。浜岡と申します。
Thank you very much for the kind introduction. I'm Hamaoka. I teach marketing at Keio University, Faculty of Business and Commerce. I was majored in engineering and I studied the nuclear physics for 2 years at the graduate school of the university. There are many noises about Fukushima. For example, 100 millisievert below can have the impact or not. What is the 100 millisievert significance? This is just an example. However, the point is that data is available. I am a scientific major. Also, I'm a professor of the Faculty of Commerce, but I'm good at using data to get the result of the marketing, and that is my overall direction or perspective. And therefore, speaking of the data analysis, I can point out several problems as I have found in my research, and therefore, I'd like to make the report on those limitations and the problems. The data disclosed so far. Now, Hiroshima, Nagasaki, Hanford, and Fukushima has a common factor of being exposed to radiation, and each site has disclosed data, and therefore I used that disclosed data for reanalysis. That is a specific topic, and I'm going to cover these agenda items today. Now, you see, I'm going to cover very, very technical subjects. However, in order to alleviate your pain to digest such technical topics, I'd like to give you the introductory part of the analysis studies. Sorry for talking about such the statistics or analysis ABC in front of experts, but I'd like to give you the brief introduction, and then I'd like to talk about the limitations of studies, and after the analysis of ours, what are the significance of those limitations and problems? After that, including Hanford, because the atomic bombs survivors data is available actually at each individual level. Data has been accumulated, however, in order to ensure anonymity, partly due to this issue, only the aggregated data is disclosed in many cases. However, this process of aggregation can cause many problems, including the lower power statistically, and therefore I'd like to talk about the significance of how problematic to aggregate data, tabulate data. In the case of the United States, individual level data is disclosed, and therefore we can apply individual analysis. And what we will see, I'd like to share that result. And then a bit out of the subjects, but I'd like to share the disclosed analysis of Fukushima thyroid nodule data. That is the part 3 of my topic, and this is the research objectives. First of all, critically examine methodologies of analysis reports that seem to be standard approach in radio epidemiology. By conducting reanalysis of the LSS14, we can elucidate the above-mentioned problems and limitations, because now, as I mentioned, there's a significant problem of aggregating individual level. That's why we've determined to use the United States data to reconfirm the data disclosed so far, and I'd like to talk about the thyroid issue. First of all, the introductory part of the A-bomb survivors. Since the 1950s, RERSF or ABCC has accumulated the data of A-bomb survivors. 94,000 A-bomb survivors and 27,000 people who have entered into the city, though they were not existed at the time of A-bomb explosion. By accumulating this data for each 5 to 10 year interval, report has been made. And this activity has been kept so far since the 1950s. The latest and main report was issued in 2012. That is what we call LSS14. This is a lifespan study, or LSS in short. Therefore, let me use the word LSS13 or LSS14. When I say LSS13, it represents the report issued in 2003, and when I say LSS14, it is a report issued in 2012. Now, first of all, this is a summary of LSS14. On this side, you can see the dose. And then at each dose category, you can see how many people were existed. And 86,000 people get the estimated doses, and therefore the analysis population is 86,000. Out of 86,000, about 50,000 people have passed away, out of which, in total, 10,000 people have passed away due to solid cancers. And if you look into each dose level, as you see the numbers in bracket, this the bracketed number shows the how many people have died away due to the solid so each doses. For example, as you see, as the dose goes up, the mortality due to the solid cancer goes up. So is leukemia. This is the basic analysis method, and if it can be visualized as a graph, it can be shown here. So whether you use linear or whether you use this curve, it's just that difference. At each dose level, you can see the percentage of Hiroshima as well as Nagasaki female-male ratio, as well as the ages of when they were exposed to radiation, and therefore not only doses, we also have to consider these variables. And then this is actual disclosed data. If you go to this URL address, and if you register yourself, you can download this data very easily. As you see here, there are 22 categories for doses, and this is data of cities, sex, age, exposure, attained age. And as to the age, there is a 5-year interval. For example, based on the data, if you plot this data, it can be explained like this. So you can see the person who have died due to the solid cancers in percentage, and this size of a circle represents how many people have died away at each dose level. In the simple manner, in the previous graph, there is a clear line. However, if you look at actual data, there are quite large varieties, and therefore we have to see the dose.
これは、被爆とともに、固形がん死の割合が増えると。
As the dose response curve, and what kind of model we have to use, we have to be careful about that. For example, this is what we call linear loss ratio level, and that is shown in red level in the format beta 0 plus beta 1d multiplied by d. D is dose. The important thing is that beta 1, this parameter, is very important because, as you see here, if 1 gray exposure goes up, how much percentage of people who die due to solid cancers is represented by the parameter of beta 1. Statistically, another important one is that beta 1 is 0 or not. That is very important statistically. If beta 1 is 0, that means that this line is flat totally. Beta 1 is 0, and then exposure level D, regardless of the D dose level, there's no change of the height. And therefore, if you apply tests in many cases, the important factor is whether beta 1 is 0 or not. I expect only the linear relationships, however, in the analysis studies, there are several functions. For example, this is a linear function, and this shows dotted line, shows a simple threshold model. Up until D0, there's no impact. However, the above D0, in a linear way, there is an impact. This is a threshold model. And then LSS14 has new estimates. That is the linear spline model here. Above or below a certain threshold, the steepness or angle of the line is different. In addition to that, non-linear quadratic curve. This is a simple quadratic model, and this is the linear combined with quadratic model, LQ in short. Therefore, we call this LQ model and Q model respectively. This is also used for the LSS14. So these are the functions expected. However, without any function estimated, you can use another model that is dose category dummy model. As to the modeling, this is the modeling applied to LSS14. Now, this is what we call excessive relative risk, or ERR. With that exposure, there is a certain level of mortality rate due to the solid cancer. And then how much percentage of people who died of solid cancer goes up. And therefore, in this formula, this red item represents excessive relative risk. And then as to the dose response curve, it's shown this. And then there is a sex difference, age difference. Although the dose level might be the same at 1 gray, those variables should be considered as a characteristics, and therefore we apply these characteristics to the dose response curve to adjust. Now, as to the characteristics of the person exposed, it's shown here, age and sex. Age means at which age that person was exposed. Suppose that that person reaches 70. How likely that person will die due to the solid cancer? That is the basis or assumption for the model. And then this is the result of the estimation.
So 0.42 in colon zone. So there's a 42% increase of the solid cancer death when there is exposure. So there is a standard error. So there's a sample of the 86,000. There's a possible error. So that's evaluation with standard error. And t-value, so 0.42 divided by 0.05, that's how we get 8.4. Once t-value is decided, then p-value will be automatically generated. So p-value means that the coefficient is 0 or not. That's an important point. When the coefficient is 0, so it's a null hypothesis. So based on null hypothesis, t-value. So what's the possibility that the t-value is 0.8? So that's a chance, a possibility. So it's very low possibility. When coefficient is 0, so less than 0.001% when the t-value is 0.8. So this means that we have to reject the original hypothesis. So meaning that we will reject the hypothesis that the coefficient is 0. So that also means that it's not the coefficient is 0. As dose increases, then the cancer death will increase. So based on that, we can say that. So with what can we reject the hypothesis less than the 5%? That's generally the consensus that we can reject the hypothesis. So when p-value is less than 5%, then we see the stars. And confidence interval, so with the chance of 95%, the true value falls into this. So as a checkpoint, we have to check to see 0 is included in this confidence interval. So in this case, p-value is less than 5%, we see stars. So the confidence interval doesn't include 0. So this means that exposure and cancer death are significant in terms of the statistical analysis. And in Asia, the exposure is negative. So when the older one gets exposed, then it's less likely for them to get cancer. So when children get exposed, there's a higher risk for them to die of solid cancer because children are more susceptible to the exposure. So that's information we can generate. And also the attached age is negative. It looks like the older we get, the more people likely to get cancer. But even the actual number increases, but the percentage of people who die of cancer due to exposure. And by age, female 1 and male -1. So this means female is more likely to be affected by this. And this is a plot of the information I just covered. So attached to the age on the horizontal side and also vertical side, ERR divided by gray. So 0.42 is here. So at the age of 30, when one got exposed, and this is a chance of cancer death at the age of 70. So this means 10 years old, 30 years old, 40 years old, and 50 years old. So the younger one gets exposed, there's a higher risk for them to get cancer. So they have done an amazing analysis. But if you look at the details, there are the following issues we can identify. I don't have time to cover all the details, so I just look at the issues with the aggregation of individual letters and also sample limitation and also selection of incomplete model. So those are the 3 topics I'd like to cover for today. So using all the data, we make an assumption or estimation. LSS 13 data. This is the limitation of a dose range. The first one is 0 to 0.05 sievert. So using this group, they did the assumption, they did the estimation, p-value 0.05 no stars indicated. Likewise, up to 0.1, 30% no stars. And 0.125, then p-value becomes 0.025, 2 stars. So meaning this is the beginning of the significance. This means 100 sievert, less than 100 sievert. Statistically significant impact has not been observed. That's the basis or logic. So there's so much data available, but why are they looking at this portion only? That's the sort of arbitrarily way of selecting the data. They should list all the data available, not just this portion of the data. So in this thread, there's different slopes. So we have to do estimation based on linear spline model that's more accurate. LS13, this kind of analysis was done, but for LS14, this analysis wasn't conducted. So those people who used LS13 realized there's a problem or issue with this. Unscare, unfortunately, did the same method in 2006 report. Well, that was a simple model used, actually. But there's a standard error in the dose estimation. This is rather more difficult, more complicated. And they limit the number of dose range and samples. So up to 250 millisievert. Sorry. So as for the cancer that's up to 200 millisievert, we started to see the star signs, and also up to 250 sievert. Then we started to see solid cancer incident. So at the level of 100, we started to see the significant statistical number. So by limiting the number of samples, so this is not a good way, statistically speaking. So that's how, or even in such an important report, they use such a method. That's unfortunate. And the second issue we have is a selection of incomplete model. So here, linear model, linear plus quadrant model. So this dotted line, that is based on dose dummy category. LQ model, they conducted likelihood rate test, and linear model is the best based on this likelihood rate test. There's no model comparison with the dose dummy category. So here, so circle goes into the negative area. So looking at this one, so at the low dose, risk goes down. So there's a hormesis effect. So some people use this to prove hormesis effect. So likewise, LSS14 line spline model is used. So above or below boundary, so there's a different slope of lines. So they change the value. They look at how the parameter moves as the number goes below the boundary. That's indicated in black dots. You see the line or arrows. That's a confidence interval. So around this area, 200 millisievert or 200 milligray, up to that level, then 0 doesn't go into the confidence interval. So by looking at this number up to 200 sievert, it looks like this is the threshold based on this data. But with this model or the linear model, which one is more appropriate? There's no fitting testing. So in LSS14 abstract, that says, I have 5 minutes left. Well, I just made a wrong time management. So it looks like a line model is better. Well, it looks like that's what it says. But in the second half, it also mentioned threshold model. So it looks like a threshold model is also supported by this journal, but threshold is 0. So as a result, it's difficult to see what the actual conclusion is. So it's not good. That's why, well, they analyze different models this way, and they use the likelihood rate model, but there's no comparison with other models. So on top of their models, we introduced another testing. They saw all the data. They look at LQL model, but they just focus on 2 gray zone, and then LQ model is better in terms of fitting. That's their conclusion. But so why 2 gray? So that's a question. Well, there's no validity of using 2 gray. If they use that criteria, then they use all the data, and if they can see the change of the function at the 2 gray, and This is the model to estimate estimate the threshold statistically. AIC or BIC, there's a criteria to use the AIC or BIC. If we use that criteria, the red number is a better fitting. So with the linear model or manual threshold model, if it's less than 50 milligray, then the same level of fitness is guaranteed. When it comes to linear model, well, the threshold can be tentatively decided by the researchers, and we can just see how it goes. It's a rather primitive method. If we try to estimate the threshold itself, well, it's possible. But compared to that method, with AIC or BIC, linear model has a smaller number. So based on there's a threshold, linear model is better.
Therefore, in case of
を前提にすると、線形モデルが最良であるということは、ちゃんと
so then appropriate model selection should be conducted, and then we can say that the linear model is good. Another point I have to say, as I'm running out of time, therefore I skip the remaining part. At any way, we have done many Oak Ridge, Rocky Flats, and Hanford by using three sites data because they have individual data. Just like LSS, stratified data is used for analysis. There are such populations, and based on that population analysis result, as you see here, there is no asterisks, meaning that for all the causes of deaths, there's no significant relationships between the radiation exposure as a report. However, the hazard level and the binomial logit as well as the multi-item logit. If you look at the individual level by using this method, now you can see asterisks. And therefore, depending on what kind of models you use, maybe the statistical power is declined, as we can assume. And therefore, in order to evaluate low dose exposure, rather than aggregating all the available data, you have to take a look at the raw data at an individual level. That it will give us better results. I believe this is an important message I have to share. As to the siloed data derived from Fukushima population, I cannot cover everything at any rate. Primarily, screening has more robust data. Therefore, I use that for my analysis, and this is a result. This is 2 times before that, and a suspicion of malignancy in 3 years. The 109 cases were malignancy or suspicious cases. 109 in 59 local municipalities, and therefore, because N is too small to ensure the power. However, if you look at nodules, there are about 1,000 to 2,000 nodules identified, and therefore, there is a possibility of confirming significant difference statistically. Then in the past, what kind of studies were conducted? I studied them. For example, if you look at A-bomb survivors and their exposure level, now the relationships between the cancers and the exposure level has positive relationships. Not only that, if you look at nodules, there is the positive and significant relationships. And if you look at medical radiation exposure, you can see the same trend. And then in the follow-up observation, follow-up study, just one time, though, at one point, we have conducted thyroid screening, and there are 82 people get screening, and there is no observation, and there is the person who got the cyst. And you can see numbers here. As to the control cohort, the ratio is 0.3%, and this is the ratio of onset of the cancers. However, in the nodule cohort, the ratio of cancer onset is 7.3% according to the result, meaning that the nodules can be the predictive marker to tell us that person may develop cancer in the future. In that sense, we analyze nodules, or analyzing nodules might be significant or meaningful. There are many doses, however. This is data of each municipal area's estimated exposure on thyroid for the children below 10. You can see the plot for each local municipalities, and then now you can see the increasing trend linearly. And then this shows the ages of screening on the x-axis, and you can see the size of nodules on the y-axis. And this is the malignancy or suspicious cases. You can see the relationships between the exposure age and nodules, or the relationships between the exposure age and malignancy or suspicions. As to the exposure ages, it's go down. Especially, it's remarkable in this graph. That means that if exposure happened at the young age, or the younger the exposure is, the higher the malignancy is. This agrees with the result of LSS study. Based on this study, I applied a Poisson regression, and this is the result. First of all, as to the small nodules, the thyroid exposure is positive, meaning that significant because there is an asterisk. As to the large-scale nodules, it's positive, and therefore, if we combine the small and large nodules, it's positive. However, there's no significance for the cancers because the just n is 100 is too small to have a good power statistically. And then this is the exposed age that is negative, and the attained age is positive, and disagree with the LSS data. Based on that, as we predict from the leading studies, we obtained the result agreeing with the previous studies. As far as the nodules are concerned, there is a significance to relationships between the exposure level and the nodules and the cancer onset. Therefore, we have to have better studies. And the N is 109 in addition to the controlled cohort. Such a case control analysis should be minimally required. I skipped part of my presentation, but as to experts, although they are called experts, but they don't have much knowledge about statistics. Experts have to study. As to the analysis, instead of the aggregated level analysis, we have to use individual raw data that will give you more meaningful results, especially in order to evaluate low dose radiation or low dose exposure consequences. You have to look at the individual data. And the individual study is conducted, reviewed by Anscare, and put together as reports. And then ICRP issues recommendations, and sometimes the criteria is set up. This is the mechanism in this community. However, it takes a long time, and therefore, the supporting data of the current recommendation is LSS 13. This was conducted 13 years ago. And therefore, we have to incorporate and reflect the latest findings and expertises as soon as possible. However, it may be too difficult to change this mechanism, and that's why it's also more important to understand that at least current policies are based on the very arcane and obsolete findings, and therefore we have to try to use the precautionary principle by incorporating new expertises and findings. That is my message.
Well, thank you for that, I might say, mind-blowing presentation, because the amount of data you have presented to us today is certainly more than my mind can accommodate in the time. Can I just seek a clarification? You are not favoring a threshold, is that correct?
Pardon?
You are not in favor of a threshold for solid cancer, for example?
Yeah.
Not in favor?
Not.
Yes.
Yeah.
Okay. it's open for questions, but bearing in mind more clarifications than deeper questions, we have a session for questions later on. So, yes.
My name is Segawa. On page 33, you can look at the results or conclusion. Analysis of individual data is more efficient, effective. So that's an important key message for you. So why is it important? You didn't have time to cover the details of why individual level analysis is more efficient. So generally speaking, for one thing, for LSS, they're just looking at cancer. But other than cancer, there are deaths other than cancer. So that's one of the reasons. And by age or by different category, so you do an categorization analysis, but LSS does some level of the category-based one, but you have to look at the individual later. So they re-aggregate different levels depending on the range of the data. So without having individual data, but that's why LSL can't do an individual level data, even though they want to change the values. So is my understanding correct? So when it comes to individual level data, let me go back to previous slides. Can you see this? For example, this is a raw data, and 1, 2, 3, 4, 1 to 10, they're individual data. And that's raw data at the individual data. That's what I mean by individual data. If we look at variance, 1.17, and by stratification, we put them into two categories. So that's the example at the bottom. It's a very simplified example, but from 1 to 5, there are 5 people, and from 6 to 10, there are 5 people. Well, there are 10 samples. We just put it into two categories. So that's what I did. That's what I mean by the aggregation of individual data by category. So variance was reduced from 9.17 to 6.94. So there's the information loss from the previous raw data. When we do testing, I said a beta 0 or not is important. So we use a t-value for this testing. If you look at the formula, variance D is included in the formula. So this is dosage variance. So this is the same as this one. So by changing dosage category into multiple categories, so there's a loss of individual data, and that's why t-value goes down. Then it's hard for us to reject the hypothesis that the coefficient is 0. So that's what I mean by there's a problem with the aggregation of individual data that leads to the information loss. My name is Yoshida from the pediatric doctor. Thank you very much for your presentation. I have a question about LSS. LSS has no control group. And the dosage, well, I thought based on the presentation you did today, you mentioned subgroup. Like if you focus on children with the more sensitivity to exposure, so even it's less than 100 millisieverts, then there will be a significant results statistically. If we do categorization, then the total sample will go down. If we focus on children, well, I don't think it's better. It's a good idea to do and focus on categorization of information into, for example, children. As you saw in the graph, we should use all the data, and we put the age at the exposure. Then the age at exposure becomes negative, so that means this is significant data statistically. So when the age at exposure is 10 or 20, 30 years old, so this is a risk of cancer death. So the younger at the exposure, the higher risk for one to get cancer. So I think that's sufficient. What do you think? I'm starting on 100 millisievert threshold. So as an assumption, there is a same linear model. There's the same dose response model. So this will be modified or adjusted by age slightly. So based on linear model, I did the estimation or analysis. Well, the significance. Well, there are several models for estimation. AIC or BIC are being used to select to the selection. So linear model is the best in consideration of age at exposure, also attached age. So linear model was the best model based on this analysis. Additionally, looking at LSS data, as for the solid cancer in 1958, that's when we established this method. So when cancer occurred before that age, then we didn't consider that. But even so, when one is younger than 20 years old at the exposure, well, there's a significant result in terms of the thyroid. And I've seen other significant data, but I just confirmed the significant result for the thyroid cancer.
For a very interesting presentation. And we will take a break now until, let's say, 25 to 12. And we'll resume with the next paper. Thank you.